Okay everyone, we're now going to talk about antiderivatives. Kind of sounds like against derivatives or maybe opposite derivatives, right? Well, that's kind of correct. And I'm going to cheat here. I'm going to use part of an old video. So in a second here, we're going to make a hopefully smooth transition to an old video, and then I'll be back for the second page to finish things off. You might not even notice. So I have a question for you. If y equals 3x to the fourth plus 2, then what does y prime equal? Well, that should not be a problem at this point in the game. We're just taking the derivative of this, just have to use the power rule. Bring the 4 down, multiply by 3, we get 12x cubed. And of course, the derivative of a constant like 2 is 0, so don't even need to put it. There you go, finished. But what if I gave you the derivative? What if I told you that y prime equals 6x squared? Could you figure out what y equals? Could you figure out what the original function equals? Okay, instead of this 2 dropping down to a 1, as normally happens when you do the power rule, what's going to happen to the 2? It's going to go up. It's going to become x cubed. Alright, well, what number is going to have to go up front here? Well, I think if you look at it a little bit and do a little bit of calculation, you could figure out that what should be up front here is a 2, right? Because if you do the power rule, if you go to the opposite direction, 3 times 2 is 6x, and this would drop down 1 to 2, so 6x squared. So there you go. But here's the thing. There could actually also be another piece to this, couldn't there? You could have plus, and what could go right here? Anything, as long as it's a constant. So I'll put C, and then I'll write could put any constant here. So what we just did here, where we started with the derivative and found the original function, if you want, this takes us to the idea of antiderivatives. What an antiderivative is, it's also called indefinite integrals. It's the reverse process of differentiating. So that's probably the easiest way to think of it. You're just doing the opposite direction. But mathematically what that looks like is if f prime of x, so if the derivative of capital F equals little f of x, then, now here's a new symbol, f of x dx equals fx plus c. Whoa, what's going on here? What's this all about? Okay, this big S looking thing, this is called the integral sign. This alerts you to the fact that you're going to take an integral. You're going to take an antiderivative. The f is the integrand. It's like the function that you're taking the integral of. The x is the variable of integration. The c is the constant of integration. Capital F of x is the function you end up with. The only thing we haven't talked about that yet is the dx. As for this dx here, I'm going to give you a very unsatisfying answer. You can think of it as, for an integral, there's the starting sign, which is this s, kind of, I think it comes from sigma, but I'm not going to get into that either. But there's this sign here, and that the dx is kind of the ending part of the notation, and that everything in between, the fx, is what you're taking the integral of. So that's a very unsatisfying answer. This idea that this is just like a full stop at the end of it. There's actually a more complicated, I would say quite a bit more complicated reason for this. It has to do with we're taking smaller and smaller pieces of x, and we're looking at the area of different rectangles under a curve. I just don't want to get into it right now. Okay, you'll learn about it in university. We can talk about it in class. but I'm just going to leave it for that. Okay, so in other words, I'm just going to say again that think of it, I think for now, even though it's not a totally satisfactory or correct answer, a lot of people, actually I think I went through all through university and never always thought of it this way, is that this is your starting and this is your ending of the integration notation, and anything in between those two highlighted bits is the bit that you're actually taking the integral of, that you're actually taking the antiderivative of. Okay, let's move on. So some commonly encountered antiderivatives. If you had the function 0, what would be the antiderivative? So in other words, you know this already. What sort of function, when you take the derivative of it, do you get 0? Well, we already talked about that. When you take the derivative of any constant. So a function of 0 has an antiderivative that's a constant. What if you have a function of 1? Well, what do you have to take the derivative of to get 1? You take the derivative of x. So the antiderivative of 1 is x. Okay, here's a harder one. What's the antiderivative of x to the n? Well, you know it would be x to the n plus 1. But would that be it? No, it wouldn't actually. Let's go back up here. Remember this example we said right here, this 6x squared? If all you did was raise that 1 and put 6x cubed, you wouldn't have the right answer. You need to end it with a coefficient of 2 here. So to see what you'd do to the 6, you would actually divide it by that same amount, by 3. And this will work every single time, as you shall see. So it's going to be x to the n plus 1 divided by that same amount, n plus 1. In fact, let's take a look at one of those right now. Let's say we want to take the antiderivative, or the integral, of x cubed. Okay, so remember, the s and the dx just tell you we're taking the integral. It's x cubed, which we're actually taking the integral of. So according to this formula, what I do here is I would raise this 3 to 1 more, which is x to the 4, and it would also divide by that same amount. I divide by 4. So is that correct? Well, let's think about this for a second. Let's go the opposite way now. If we were taking the derivative of this, what would you do? You'd move the 4 down. The 4 would now become a 3, and it would still be, of course, over 4. Hey, wait a minute, those would cancel, you'd have x cubed. It worked. So this will always work, this formula that we have right here. Before I go any further, let's just make sure you're clear what we're talking about. What we're saying is that if I'm taking the integral of 4x cubed, or the antiderivative, same thing, if I'm taking the antiderivative of 4x cubed dx, the answer to that would be what? Well, you'd raise this to the 4th power, so you'd have x to the 4th, and you'd also divide by the same amount, so the 4's would cancel. This would be your answer. If you're not clear about that, try going the other way. Try taking the derivative of this. The derivative is 4x cubed. That's exactly what we have. But you'd also have to put plus c, because remember, you could also have any constant there, and when you take the derivative of that constant, it would equal 0. So if we go this way, we are taking the integral. We're doing integration. If we go this way, this is what we've been doing this whole course. This is taking the derivative. So they're just opposites of each other. Opposite processes. Okay, let's move on. 1 over x. Which function has a derivative that's 1 over x? Do you remember which one? It's the natural logarithm of the absolute value of x. How about this? Which function has a derivative which is e to the kx? Well, you know that the derivative of e to the x is just e to the x, so you might think it's just e to the kx. But that k is definitely going to impact things. Like, let's say, for example, you were taking the integral, the antiderivative, of e to the 2x, and then I'll put that dx to close off the integral notation. Well, you might just think it's e to the 2x, right? But let's go the opposite way. If we went the opposite way, if we actually take the derivative, it would be e to the 2x. It would be the chain rule, wouldn't it? It would be e to the 2x, but then we'd have to multiply by the derivative of the inner function, so that would be 2, and that's not what we have here. So what would we have to do to get that answer? We would have to divide by 2. Oh, so it looks like what we actually have to do is we have to divide this by whatever that amount is, that k. So in this case, we'd have to divide by 2. and that would give us the right answer. Because, again, if we try, right, you can always try by taking the derivative. You'd have a constant of 1/2, so you could just write that, right? Then you'd have e to the 2x, that's your outer function, and your inner function, the derivative of 2x is 2. Hey, this and this would cancel, you'd have e to the 2x, and that's exactly what we wanted. So this is our formula for when we have e to the kx. Cosine of kx. Okay, so what do you take a function of and you end up getting cosine x? It's sine x. If you take the derivative of sine x, you get cosine x. But wait a minute, this is cosine kx. So let's think for a second. Sine kx. Why don't we try taking the integral, the antiderivative of cosine 3x dx. So again, you think, okay, well, it would be sine 3x because we're going in the opposite direction. But this isn't the right answer yet, is it? Because again, if we went backwards, if we took the derivative of sine 3x is cosine 3x, but then you'd have to multiply by the inner function, the derivative of the inner function, which is 3, and we don't have that 3. How come? Because we must have divided this by 3. So your formula for this is sine kx over k. Okay, sine kx. You might think this is just cosine kx, but remember, cosine, when you take the derivative, it's going to be negative sine. So in order to get sine, you must be negative cos. And again, that's not enough. You're going to see that you have to divide by k. Let's take a look at that. If we had sine 2x dx, so again, you might just think it's cosine 2x. Let's start with that. But when you take the derivative of cosine, you get negative sine. We want it to be positive sine. So it must be you must need to have a negative here. So when you take the derivative of cosine and get negative sine, negative sine is positive sine. Make sense? Now, even this isn't good enough, because taking the derivative of this would give you positive sine 2x, but then you'd have to multiply by the derivative of the inner function, which is 2. And we don't have that 2 there. How come? Because we must have divided it by 2. That way, when we multiply by the 2 from the derivative, it cancels out the 2 in the bottom. So this is why you have that k on the bottom. Okay, let's try some examples here. Here we have f of x, which is 4x cubed minus 6x squared plus 11, and we want to find the antiderivative. We could also say we want to find the integral of this. So we often represent the integral, the antiderivative, with the capital letter of whatever the small letter is here. So I'll do that. F of x equals. So how do we do this? Well, with this one, remember, what you're going to do is you're going to raise the exponent. So we still have our 4, we raise the exponent to 4, and that same number becomes our denominator. And we do the same thing here. We raise the exponent 1, so it's now up to 3, and then we divide by that same number. And for the last one, if it's just a constant, it becomes 11x. Don't forget, we need to put plus c. Now we just go back and simplify everything. In the first one, look at the 4's cancel out. You just have x to the 4th. Minus 6 and 3 cancels out. You get 2x cubed, and the rest stays the same. You're not sure if you got the right answer? It's pretty easy at this stage of the game for you to take the derivative of this. 4x cubed. Yep, that's what you get. Negative 6x squared. Plus 11. Yep. And if you did have a constant, the derivative of the constant's just 0, so that would work too. Alright, there you go. Okay, the next one. We need to take the antiderivative of cos pi x. So if you look back in the previous page, it tells us in order to get the derivative of cos kx, it's equal to sine kx over k. Well, in this case, the k is pi. So we're going to have sine pi x over pi minus. Now, for sine x, if you look back on the other side, it equals, the antiderivative equals negative cosine kx over x. So I know I already have this minus sign, but we get another negative sign, and then our sign becomes cosine. The k in this case is just 1, right? So it's not going to make a difference. So you get x over 1, which doesn't make a difference. And don't forget to put plus c. Now we simplify. So there's nothing you can do here. Sine pi x, probably put that in brackets actually, over pi. Sorry, it doesn't look so good. And only thing that changes, this becomes a plus. And we're done. Okay, we have some exponential functions here. If you look back in the previous page, it tells you that the antiderivative of e to the kx is e to the kx, again, just divided by k. So you gotta love the exponential ones when you're taking antiderivatives. The -3, the coefficient, just stays there. Now, our k is -1, so we start by just writing exactly the same thing, e to the negative x, but then we divide it by whatever the k was, and k is -1. Plus, write down the coefficient, keep the e statement exactly the same. Our k in this case is 2, so we need to divide it by 2, and of course, don't forget to put plus c. Oh, how many times did I forget to do that on tests in university? So annoying. Negative divided by negative is positive, e to the negative x, plus 6 divided by 2 is 3, e to the 2x, plus c. Looks good. Some books or some questions don't want you to have negative exponents. If that's the case, of course, this would become 3 over e to the x plus 3e to the 2x plus c. Either one works for me. I'll circle, I guess I'll circle the bottom one. I don't like those negative exponents. Okay, this one. Oh, this looks hard. I have stuff in the denominator. Any ideas what you might do? Well, what you're going to want to do is rewrite the first one. So I'm not actually taking the antiderivative yet. I'm just rewriting this. How could I rewrite this so the x is in the numerator? You could do that if you make it 2x to the -2. I just talked about not liking negative exponents, but sometimes you do like them. Sometimes it helps you. Now, should I do the same thing for this one? Well, you can, but one thing you should hopefully get used to is that if you're taking the antiderivative of 1 over x, it equals the natural logarithm of the absolute value of x. And we have this situation right here, right? I know it's a 5 and not a 1, but the 5 is just a coefficient. This is like 5 times this 1 over x. So I would just leave this. In fact, you could even write it like this if it helps you picture it a little bit better. And then our plus x is fine. So I haven't done any antiderivative here, no integration yet. Now I'm going to do the integration. So here we go. How does it work? Well, in this case, you raise the exponent by 1, so it's up to -1 now, and then you divide by exactly the same thing. For the second one, we'll keep that -5, and then we just said when you take the antiderivative of 1 over x, it becomes this. So that's what you're going to get for this piece here. You're going to get natural logarithm of the absolute value of x, and this is x to the 1. So again, you want to raise the exponent up by 1, divide by the same thing, and slap on a plus c at the end. Now we go through and simplify everything. So 2 divided by -1 is -2. Hey, want to get rid of that negative exponent? Why don't we throw that x into the denominator? We got rid of that. Minus 5 times the natural logarithm of the absolute value of x. Nothing we can do there. In fact, there's nothing else we can do in the whole question. So we are done. Okay, moving along here. I would probably switch something here. So again, I'm not taking the antiderivative yet. I'm going to keep the first one the same. I know I can take the antiderivative of that. Same with the second one. No problem there. But this one, you'd probably rewrite that how? X to the 1/2. Okay, now we can take the indefinite integral or the antiderivative. So what do? Raise this exponent up 1. So keep the coefficient, raise the exponent up 1, divide by the same amount. Same with the second one. Raise that x3 to an x4 and divide by the same amount. But wait a minute, there's already 3 there. That's fine. You already have the 3, and you're also now at the bottom have a 4. Got to multiply those. Plus, got to raise that up by 1. Well, 1 more than 1/2 is 3 halves. Don't put 1 1/2. Keep them as improper fractions, and then you divide by the same amount, 3 halves. Ew! Look at this complex fraction here. We'll get there. And then plus c. Okay, in the first term, there's nothing you can do. So we have 2x to the 5th over 5, or you could write that as 2/5 times x to the 5th. That's fine too. The second one, you can just multiply the denominators. So 3 times 4 is 12. Now, you're clear how this works? If you're dividing, right, this line right here means divide, you're going to multiply by the reciprocal. So I'll just do this one time. It's kind of like you have x to the 3 over 2 multiplied by the reciprocal of 3 over 2 is 2 over 3. And you'll see this bottom number is going to end up back up top. That's what happens when you divide by a fraction. The denominator comes back up to the numerator, and the 3 here will become your new denominator on its own. So hopefully that makes sense. Plus, so we have the 2 popping up to the top, 2x to the 3 over 2. I think we can just leave that as 3 over 2. Of course, we could write the square root of x cubed, but let's just write it like that. And on the bottom, we still have a 3 plus c. And the last one, what we're going to do here, we got stuff in the numerator and stuff in the denominator. That's okay. Just look at it like we're going to consider this and this separately. Put them both over to x separately, right? If it's 7x cubed plus 3 over x, that's the same as 7x cubed over x plus 3 over x. So let's do that. So I'm just going to rewrite it first. So h of x equals 7x cubed over x plus 3 over x. All right, I can actually simplify the first one, right? It's 7x squared plus, there's that situation again where we have just the x in the denominator, kind of like right here, right? Remember this 5 and the x? So it's kind of the same thing. So if it helps you picture this, this 3 over x is the same as 3 times 1 over x. I mean, I don't think you need to write that, but if it just helps you in this first video here to understand why I'm going to do the next step, then I'm going to write it. So we're going to take the antiderivative, the integral, raise the exponent up one, and divide by the same amount, plus 3 is the coefficient, we keep that. Now, what's the antiderivative of 1 over x? Get used to it, it happens all the time. The antiderivative is natural logarithm of the absolute value of x. And then we got to do plus c. I don't think there's anything we can simplify here, so I'm able to circle it already. Love it. Okay, there you go everyone. Antiderivatives, indefinite integrals is also the name for them. Next day you'll get the shocking lesson that will connect the area under curves with antiderivatives. Oh, I love it. See you then.